Hey everybody. So as promised, I decided to make a review video of the notes that we took the day before the break. So we were talking about section 9, which was graphing linear functions. This is also mixed with a little bit of the beginning of section 10, which is on intercepts. So we were a little bit ahead, which was nice. And it was also a review from the beginning of the semester because we did talk about these things in other situations. So it's nice how it comes full circle. So in order to understand what we're talking about with linear functions, we have to understand what it means to be linear. Hopefully this is a reminder for those of you that were there. Linear, okay, look at the word. It has the root of the word line. So we are talking about straight lines, okay? The words often help us to figure out what we're talking about here. So we're going to do a threefold definition. We're going to talk about the definition of what it means to be linear graphically, numerically, and symbolically. So graphically, we pretty much already talked about. Graphically means we're dealing with straight lines. When we look at the graphs, we're going to be straight lines, okay? When we connect the dots, we can see an obvious pattern straight. When we're talking about a table, we're looking for a pattern. We're going to notice that for every constant change in x, there is a constant change in y. It doesn't mean that they have to be the same change. It could be a change in 2 and a change in 3, for example, but you will see a constant addition. For every 2 increase in x, there is a 5 increase in y, again, just for example. But you're going to notice that there is a constant pattern in the columns. And then last but not least, we're talking about how can you tell just by looking at the formula that you are dealing with a line. The input and output variables can only have an exponent of 1. So in layman's terms, we're talking about a plain old x and a plain old y. That means that you're not going to see any other exponents on x's and y. You're not going to see any square roots. You're not going to see any variables in the denominator. Nothing weird is going to be happening to the x or the y. Okay, going to be a regular x and a regular y in the formula. And another thing to note is that the solutions that we're looking at are ordered pairs. We're going back to inputs and outputs, just like we did it from the beginning of the semester. So we're going to be writing and plotting everything as an ordered pair. Then we looked at the different orientations that a linear function could take on. Here we have a straight line that is tilted upward as we move from left to right. So we would call that increasing. This is an increasing line. Here we have a line that is tilted downward as we move from left to right. So we're talking about a decreasing line. And here we have a perfectly flat horizontal line. So it's not increasing and it's not decreasing. We would call this a constant line. Now, the one orientation that's missing is a vertical line. And the reason why we put that separately is because a vertical line can't be classified as a function. Okay, why is it not a function? Because if we go to this particular x, this particular input, it has infinite outputs. It has all of these different output values. And we know that that's not a function because we know the definition of a function is that every input can only have one output. So this is not going to represent a function. As a matter of fact, we're going to see in later videos that this is going to have its own type of equation. Then we went to some examples. So here we have the equation y equals 2x plus 5. How do I notice that this is linear? This is linear because the x and the y are raised to the 1. It's a regular x, x to the first power. It's a regular y, y to the first power. So I know that this is going to be a linear function. Then we went and we made the table. This is a blast from the past. This is what we did at the beginning of the semester. So you get to choose input variables. So the inputs we chose here are -2, -1, 0, 1, 2. You can pick whatever you want. Some of you just prefer your go-to 0, 1, 2, 3. Some of you might want to do something else, and that is okay. These are your choice. I highly recommend that you always include 0 as one of your choices. Other than that, it doesn't really make too much of a difference. How do you fill out this column? Well, I have to plug in -2 into the function in order to figure out what's going to go in as the output. So over here is where I showed that work. Everywhere I see x, I'm plugging in -2 in parentheses so that I can work it out. So this is 2 times -2, which is -4, and then -4 plus 5, and that's what gives me +1 as the output. That gives me the ordered pair -2, 1. And then I just keep doing that for every input that I've chosen. So here I'm going to plug in -1 everywhere I see x and work it out. You should get 3. And then here's the rest of the table. And you can do these calculations in your calculator. You don't have to do them by hand. How can we tell that this table is in fact linear? Well, if we go back to that definition that we just talked about, there has to be a constant change being observed. Well, here, as x increases by 1, because all of these are differed by 1, so as x increased by 1, y increased by 2 every time. This is +2, +2, +2. If you can observe that kind of pattern where you have the same change, okay, a constant change going all the way down the x's and all the way down the y's, that relationship of a change in y to a change in x is what we're going to look at for a linear relationship. So I do notice that pattern, which tells me, oh, yep, again, that's going to be linear. And now the third way is if I plot these points and they all connect to be a straight line. So I plot all 5 ordered pairs, and sure enough, they lie on a straight line. Okay, so we got, again, 3 ways to decide if you have a line. Another example that we did before the break. Here we have a fraction thrown into the mix. We have y equals 1/3 x plus 3. Look at what's happening to the x. X is being multiplied by a fraction. We know that multiplying by 1/3 is the same as dividing by 3. So we would love numbers that are divisible by 3. So we can choose numbers that are easily divisible by 3. That would be all your 3 times tables, 3, 6, 9. I always recommend having 0 as one of those numbers. So the numbers that I've chosen are -3, 0, 3, 6. Again, yours can be anything. If your go-to is 0, 1, 2, 3, then you can stick with 0, 1, 2, 3. Just realize that you're going to have fractions in some of your answers. Then we do the same thing as we did earlier. Everywhere I see x, I'm going to plug in -3. If you do that directly in your calculator, you should wind up with an output of 2. Okay? Now let's go back and answer these questions about how do we know this is linear. I know that this function is linear because it's a plain old x, x to the first power, and it's a plain old y to the first power. So this tells me that I must be dealing with a linear equation. How do I know that this table is linear? Well, look at the pattern. For every 3 increase in x, y is increasing by 1. So I can see that pattern. There's a constant addition happening. So that tells me that this is going to be linear. And then last but not least, I can plot these ordered pairs, connect the dots, and I see that I have a straight line. Then we moved on to equations that might not be solved for y, okay? These equations don't have y by itself. However, I can still tell this is linear because it's a plain x to the first power. It's a plain y to the first power. But what I would like to do is get it to be y equals, so this way it's easy for me to plug in values. So I'm going to get y by itself. Subtract 2x from both sides. That's going to leave us with 4y equals negative 2x plus 12. I'm going to recommend that you keep your variable term first, but it is not wrong if you wrote 12 minus 2x. That is the same thing. I just want to try to get us into the habit of keeping our variable first because it is going to make a difference later on. Then I want to get y by itself, so I have to divide by 4. If I divide this side by 4, I have to divide this whole side by 4. So I have to divide everything by 4. So if I divide this by 4, and I divide this by 4, and I simplify, I wind up with negative 1 over 2 x plus 3. Okay, so that's just those two things simplified. Then this equation is much easier to plug in values for, so I can choose things that are easily divisible by 2. So I chose some even numbers, you can see in my table. I plugged in those numbers, the work is here, for x using parentheses, and then I worked them out, and then these are the corresponding outputs. How do I know that this table is linear? Well, as x increases by 2, so plus 2, plus 2, plus 2, y is decreasing by 1. Take away 1, take away 1, take away 1. So as x increases by 2, y decreases by 1. But I do have that constant pattern, that constant change. And then this is the resulting graph, which you can see perfectly straight line. And last but not least, we talked about intercepts one more time. This is a blast from the past from the beginning of the semester. We know that it only takes really 2 points to make a line. If you wanted to walk from one spot in the room that you're sitting in right now to another spot, the most direct way to get there is to just walk straight there in the straight line. So it only takes 2 points to make a line. Why in the world are we getting more than 2 points then? Well, we're only doing that so that we can spot the pattern and make sure we didn't make any mistakes. But always know that it only takes 2 points to make a line. So what 2 points could you find? You could find the x and the y intercepts, because we know that the x-intercept occurs when y equals 0. All we have to do is plug 0 in for y and figure it out. And the y-intercept occurs when x equals 0. And again, all that means is we have to plug 0 in for x and work it out. So the work is shown underneath each one. If I plug in 0 for y, I'm going to do in parentheses, wherever y is, I'm going to plug in 0. Zeros are nice because they cancel stuff out. So that's going to leave us with negative x equals negative 10. And when I solve for x and divide by -1, I'm going to get x equals 10. But that is not the x-intercept. We know that intercepts are always ordered pairs. So the ordered pair is 10, 0. Then we show the work for the y-intercept. The y-intercept occurs when x equals 0. So wherever I see x, I'm going to plug in 0. Zeros cancel out, which is why we like them. That leaves us with 2y equals -10. And when I solve for y and divide both sides by 2, I get y equals -5. But that's not the y-intercept. The y-intercept is an ordered pair, and it's the ordered pair 0, -5 because I plugged in 0 for x. Don't forget what the definitions were to begin with, okay? I could take these 2 points and I could simply plot them and connect the dots, and I would have the graph of this line. But my other option is to get y by itself, make a table of values the same way that we did earlier, and then plot those points. So that's what I have here. This would be a new addition to your notes because we didn't get a chance to do this last time. So if I were to plot this table, these are the points that I would be plotting. And if I extend that line all the way through, look at what I wind up with. I have a y-intercept of 0, -5, and I have an x-intercept of 10, 0. So everything should work out. It all results in the same answers. Okay, so I hope this was a good review. You can watch it as many times as you want if you need to, and we will pick up with new material in the next video. Have a great day.